Welcome everyone to using graph neural networks to embrace the dependency within your data. Hope you're all feeling sprightly and full of energy this morning. So to introduce myself, I work as a machine learning engineer at Go Data Driven in the Netherlands, in Amsterdam. I have a background in data science, worked several years as a data scientist, had a bit of an identity crisis because I really liked engineering, and so now I'm trying to combine the two, so a bit of data science and the engineering side of things. And quite recently I've become fascinated by graphs and their problem-solving abilities, which is what this talk is about. Aside from that, I'm also a really big cycling enthusiast. Some would call it an obsession. They may be right. And yeah, apart from that, I live in Amsterdam with my girlfriend and 2 cats. Sadly, I was unable to get any pictures of cats in the presentation. Couldn't quite make it work. So the agenda for today is to go through an example use case, which should highlight why graphs are useful. We'll also go into the theory behind how we do calculations with graphs and why that's advantageous compared to some other common approaches. And hopefully we'll get some time at the end for some questions too. So one of the main aims of this talk is to understand how sometimes we don't factor in certain features or dynamics of our problem, and how this can ultimately impact the predictive performance of our models. Whilst the particular example in this talk relates to graphs, there is a wider point, which I hope becomes clear, behind how sometimes the way we simplify things perhaps misses intricacies of our problems. So the motivation behind this is twofold. Firstly, one of the reasons I enjoy graphs is because they are interesting from different perspectives. That's regarding databases which store graph data. There's also the engineering pipelines, which are a bit quirky, and also the underlying models and mathematics themselves. So as a data scientist who's now working in engineering, it's nice for me to still be able to focus on all those different aspects. And after having explored the open source tools that now support this kind of work, they seem to be in a pretty mature state, and so productionizing this kind of work is more achievable now, and not something that will just remain dormant in a notebook on your computer. Secondly, so I work for Go Data Driven. It's a data and machine learning consultancy. Therefore, we are very lucky to work on a range of projects with different companies, different technologies, different use cases. And so it's nice to kind of develop a holistic view of how data projects are executed in different companies. And so one of the things I started to notice across different projects was a sort of rigidity in the way we sometimes approach problems. And that largely kind of comes from how our data looks like at the source. And sometimes we perhaps use the same approach or the same tool, same framework for different problems which have different characteristics. Characteristics that are perhaps ignored. So the best way to highlight this is by looking at an example use case. So we're in the beautiful city of London, and I want us to think about a bike sharing scheme. So let's imagine that we're operating a bike sharing scheme in this city, and we would like to expand this into new locations. So it's been working quite well in some of the locations, and now we want to further expand it. Now there's different types of kind of challenges here. One of the things we want to do is predict the demand for these new locations so we can match the supply. Or perhaps we want to categorize the type of demand it will have. So is it going to be serving mostly office workers who are going to be using it at the rush hour periods, or perhaps it's at a tourist location where you have more consistent demand throughout the day, in the summer. Quite a few different scenarios you could do with this particular use case, but we're going to focus on just trying to predict the demand at those locations. So let's think about what our knowns are. It's been a while since I've lived in London, so apologies if I make a geographical error. So we're already operating this scheme at some locations, right? So there's locations at the top, and we want to expand to some new locations, so those at the bottom. For our existing locations, we have some known demand, some values, and for our new locations, we want to predict that value. And we can obtain some characteristics, some features about our locations, something which gives some insight into what is there, whether there's offices, shops, tourist attractions, or even whether alternative modes of transport are available at those locations. And that's kind of represented by this green block. So this is quite a familiar way of framing the problem. We see this all the time. We have our data points, we have some features which describe our problem, and some targets, a natural separation of what the training data is, and then the data on which we want to do the predictions. And even outside this particular use case of bike sharing, it's quite a common way of framing a problem. And at this particular point, you can quite easily throw this into any popular classifier or regression algorithm. You can imagine the green block is your input data, your so-called X. Y is your target. So I think that works with almost any scikit-learn classifier. But what does this particular way of framing the problem miss? I think it's also important to understand why we sometimes frame a problem in this way and why this is how our data looks like. It's usually stored in some data warehouse somewhere, maybe some bucket, some flat file. It's ended up there through some pipeline, and then, yeah, perhaps it started out life in a transactional database where data is all very tabular. And there's many advantages to this approach. It's quite effective, works for a lot of reasons, but sometimes it may miss things. So I would ask, are there potential dynamics or features of this problem that we miss by this approach? Are we encoding all of the dynamics? For example, are there relationships between these data points that could contain useful information and context for this prediction task? For example, some pairs of these locations are only separated by a couple of tube stops, or maybe the new fancy Elizabeth line. Not yet used it. Good to know. So that's quite useful to know about how these data points relate to each other. But in this particular way, it's quite hard to encode that information. And also, if we think about how busy these locations are on certain days or certain times of the day, and how that impacts the other locations and how that flows, that's all quite useful information and context to try and have. But how do we incorporate our model to use it? We may think of just adding some extra features, which then tries to encode something about neighboring locations. But then this is what kind of information do you add here? This is also quite cumbersome to do. For example, some of these are more concentrated locations. They have a lot of surrounding locations. Others are perhaps more isolated. And so this particular way is, yeah, quite tricky to get that to work. And that's where graphs come in. We can see that this problem has a spatial element to it. And in fact, even if there's no explicit spatial element, the fact that sometimes our data points may have relationships with each other means we can define our problem as a graph, where we have nodes and edges. I hope the geography is correct here, roughly. I did check on Google Maps. So we've arranged these locations based on their rough location to each other. The edges between them correspond to whether or not people, in this particular use case, cycle between these two locations. Now you can see that we've simplified things a bit here for the sake of brevity. We could define an edge between every pair of these nodes, because of course it's possible to cycle from all of the locations. But for now, we're just going to assume we're only considering the very popular routes. So maybe the signal between two really far regions is really low, and we can just ignore it for now. So the edges, the relationships, they can be trivial. So a very common use case is social media, right? Whether we're friends or followers. Or it can be a bit more abstract, for example, similarity between two nodes. And in fact, what we encode into our relationships doesn't have to be a single value. It can encode many different things. For example, it could be the distance between the two locations. can be the time taken to cycle between them, the time taken to maybe get the new fancy line between them. All of which provides useful context for our problem.
Sorry, is a graph directed or is it?
It can be. This one is not. Yeah. Yeah, so we can get onto that later, but those where you have bidirectional information and different types of nodes and different types of relationships, that's still an active area of research, just because the maths is more complicated than the simple case. So we can see our edge can be represented by a vector with multiple values, and so there's a whole range of information we can encode in there. So how is this useful? We can imagine a scenario if two locations are served well by some existing public transport, then perhaps that's already a choice people can make, and there's no need to use the bike sharing scheme. But if they're quite badly connected, for example, somewhere like Camberwell, where I'm staying at the moment, public transport doesn't really exist there, or it's very slow. So that's quite useful to know in the context of the other locations. And our nodes, the locations themselves, they also have some features which describe some information about them. This could be about what's present there, whether there's retail stores, offices, a tube stop or a bus stop. And how is this useful? So you can imagine if it's mostly offices, then that says something about the type of demand it's going to have, what time that demand is going to be. Likewise with retail stores, that's also going to have its own patterns. So by now I hope you can see there's a nice use case for why graphs are useful and how we can, there's two different ways of framing the problem, and how in this particular way we can start to encode some more trickier aspects of our problem in this way. And hopefully you can also begin to think about your own respective domains and think, do my data points have relationships between them, and are we encoding them in our work? Perhaps there are no relationships, and in which case you're just thinking, what is this guy rambling on about? And so now we have this graph of nodes, which is our locations, our relationships, and our labels as before, the demand at each of those locations, and a natural separation of what we're trying to predict and what we already know. So now I want to take a bit of a step back out of this use case and talk about what types of problems we can solve once we have a problem defined as a graph. The first one is known as a node prediction, which is what we're trying to do, where we're trying to predict something at the node level. So here, for example, there's a classification example. Some nodes are 1, others are 0. The green one on the right-hand side, we want to know which one it is. It can be a real valued number or a classification. And there's also link prediction, where we try and predict something at the edge level, so whether or not two pairs of nodes have a connection or not. For example, if I was to create a social media account on Twitter, Twitter knows some information about me, they may want to try and predict whether or not I'm going to follow Trump. For the avoidance of doubt, I'm not. The process of doing this type of prediction is a bit trickier, has added complexities that you don't have in the node prediction case. So one of the challenges is, as you can imagine, in a really large graph with lots of nodes, most things don't have a relationship. It's very few actual connections, which means if you just predict no relationship for everything, you have a good accuracy. And so that bias, of course, is problematic. And so there's several approaches to overcome this by kind of some heuristic approach where you can sample which negative cases you do take and which positive cases you do take, so there's a balance. And there's the other added complexity that in graph neural networks, you typically encode a graph into some other representation, but for the link prediction, you then have to kind of decode it back into a matrix which defines the connectivity, which we'll also get onto later. And there's also graph level prediction where you have multiple graphs and you want to try and classify a graph as a whole. So an interesting example of this is from the chemistry world, where you have a molecule and you're trying to determine whether it's poisonous or not. So a molecule can be represented as a graph. The nodes are the particles, and the edges are the bonds between them, so whether it's a covalent bond, hydrogen bond. And then you try to predict whether it's poisonous, with the assumption that there's some substructure within there that determines whether it's going to poison you. Goes without saying, don't try this at home, of course. So those are the three main types of problems. There are also other problems. For example, in a really large network, you may want to try and predict which sub-region is influencing another part of the network. This is used in fraud detection. So you're trying to find out which node is in a kind of transaction situation where you have lots of money going everywhere. You want to find out which particular set of nodes are influencing others, or maybe find anomalies in there.
All your examples of graphs are trees, but do you really mean graphs? I mean, it's all trees so far.
So by a graph, I mean something which is defined with a set of...
There's no triangles, so your theory includes triangles, meaning, things going round in circles.
Yeah, that's possible.
I don't know, so...
That's possible. Yeah.
Fine, then they are graphs.
Yeah. So I've seen it being used in the academic space with regards to the fraud detection. I'm not sure if it's how feasible it is in the real case. So back to our problem, which is a node prediction in our case, where we try and predict demand at a particular node. So now we have a graph with nodes and edges, but how do we do calculations with this? And where do the neural networks come into play? So we define a few matrices in order to encode this problem to make it more tractable. First one is called the Adjacency Matrix. So if we have 6 nodes, then our matrix has 6 rows and 6 columns. And this defines the connectivity of our graph. The values are 1 if 2 nodes have a connection, and 0 otherwise. You probably noticed most graphs will have lots of zeros in this, so typically in the implementations, you don't do matrix calculations in the normal way, because you'd have lots of useless zero calculations. And so the implementations usually only define pairs of positive cases, and then do the calculations from there. So if you have a really large graph and a really large matrix, whilst the matrix multiplication is kind of happening, it's implemented in a different way. So just to look out for when you come across the frameworks that support this work. There's also the diagonal matrix. So a value along the diagonal, and each value corresponds to how many edges are incident at that node. And these two define the architecture of our graph. So ignoring features for now, but just the architecture. And usually what's done is we subtract the matrix from before, the adjacency matrix, from this matrix to give our Laplacian. The reason we do this is because L, our Laplacian, has some interesting features which make certain types of linear algebra just possible with those matrices. It also encodes the information from D and A, but in a single matrix, which is convenient. We also have our node features, so information about each particular node. Number of rows is also the number of nodes, but then the columns is arbitrary, how many ever features you use to define your node. And likewise with the edge. So how many features you want to encode in the edges, that's how many columns you end up there. So these 4 are the main matrices we need for using graph neural networks. And now you can see these are more typically shaped objects on which we can do calculations.
Sorry, I didn't get the edge features bit again. So are those additional? So those add on to the normal.
These are completely separate. Yeah.
They're separate.
Yeah, so it's only a feature which describes a relationship between the 2 nodes, whereas the node features is a feature which describes just a node. So it doesn't take into account what's nearby. Now, the reason for setting up our problem in this way is the fact that there's some spatial element to the problem. So if we take a look at one specific portion of the graph and we look at nearby nodes and edges, our assumption is that there's some useful information in the nearby regions that is useful for our problem. For example, if we want to understand the demand of a potential bike sharing scheme in this new location, then knowing about the scheme in nearby locations is useful for the new location. As mentioned before, if the two locations are already served well by other means, then that's good to know. So if we think about our initial graph, let's consider a single node. It's not very well highlighted, but the node in the middle is green, the rest are blue. How do we get that single node to get information from its surrounding locations? Let's say we want to consider a small subsection, so all nodes that are one node away from there. So there's information in the nearby nodes, but also the nearby edges that we want to incorporate into our central node, so it can gain useful context from its surrounding regions. We then want to kind of aggregate that information and use it to update the representation of the node so that it has an enhanced representation. So there are a couple of steps that are needed to achieve this, and the general idea is known as message passing. So let us consider the situation of node 5, which wants to get information from node 3 and node 6. For each node, we gather the values of the neighboring nodes. We aggregate them in some way, a sum, a mean, a max. I think here is a sum. And then we pass them through an update function, which is typically a neural network that we can train. And the new representation can have a different number of dimensions. So 3 go in, but 1 could come out, or more could come out, depending on how you want to encode the information. And when you train this network, it will then effectively learn to pass on the useful features from the neighboring locations and ignore the useless ones. So mathematically, this to kind of link the matrices that we defined earlier with this concept of message passing, just want to very quickly make a mention of this. So at the top we have what's known as the polynomials of the Laplacian, and in the example below we have the first order polynomials where omega 1 is set to 1 and everything else is set to 0. And when you work through the calculations, you'll see that that results in a node getting information from nodes that are 1 distance away. If we set omega 2 to 1 and the rest to 0, then we then aggregate from 2 nodes away. And this allows us to control how much information we want to pass to our node, whether we want to pass it from 1 node away, 2 nodes away, or just 2 nodes away, or potentially even more. And we do this in a layered way. So if I do one step of the first order, I get information from 1 node away. If I do that same step again, then my node will get information from 2 nodes away, and so on. And a bit like kind of convolutional neural networks, the architecture it's not as well defined as it is in the image recognition case, where we can just use other architectures from what's been defined. And so determining the optimal number of layers and the optimal kind of architecture it's still kind of, an area of research. It's not fully defined. And you also want to make sure you don't define too many layers, because then you dilute your graph. And then it's effectively like blurring an image to the point that it's a single color. So this is the end-to-end process that we have. We start off with a graph. We go through a number of layers where we encode, where we do this message passing process, and then we end up with a new representation for our graph. And then once we have our new representation, we can then put that into a very typical classifier and train our task. And at the point of the change representation, our nodes, our data points, have gained useful context from their neighboring regions. So we saw how the initial framing of the problem didn't allow us to make use of the relationships between our data points. But now with this graph representation and the layers we've defined, we can encode this information. We've used the local structure of the graph to pass information to other regions of the graph. Sometimes we may be doing a node prediction task, but all the information is encoded in the edges, in which case the message passing that we want to do is from edges to nodes, and vice versa. If you want to do an edge prediction task, but our nodes seem to contain the information, then you want to transmit that information from the nodes into the edges. Slightly more complex when you do it that way, because as mentioned earlier, the dimensionality of our edges and nodes are different. There's two approaches to overcome this. The first one is to create some mapping between the two spaces, or just to concatenate your features, which is usually easier. So trying to create these representations without graph theory is cumbersome. And I hope the general method is at least a little bit clear behind the logic of why we do this and how we can define our problem as a graph. But ultimately, the core assumption has to be there are some relationships between our data points that are significant enough that we have to go through the hassle of doing this. So performance-wise, most research papers now just compare different graph approaches with each other. The earlier ones in 2017, 2018 included comparisons between graph approaches and non-graph approaches, which is quite interesting. So in this paper, they do this task of predicting traffic flows. On the top part of the graph, you can see some of these performance measures, the MAPE and the RMSE, and you can see they're a little bit higher than what we can now achieve with graphs. The bottom one being the latest innovation at the time, which is a significant improvement over previous approaches that don't encounter this. So now I want to spend a bit of time talking about the practical side of this, the technologies and the processes of getting something like this working. The implication is not only for data scientists, but also data engineers. Because getting something like this working in a notebook is fine, but then to productionize it with smooth pipelines, machine learning pipelines, is not as straightforward as it might be with other models and approaches we use. But as I mentioned earlier, the tools to support this are pretty mature. So for your database, Neo4j is probably the most well-known graph database. AWS and GCP, I believe, offers managed services of this, so you don't need to hire some specialized graph database engineer. I think AWS also has Neptune, its own version of a graph database, so I'm not sure how that fits into their ecosystem. And effectively, the difference between a traditional database is that we store the relationships explicitly in the database. So usually when you write to the database, it takes longer. But then at the query time, it's quicker because, well, as shown by here, if we want to get a list of customers who bought certain items, in this query above, you can see we have to define the joins. And the query below, we don't explicitly define the joins, we just define the relationship between our two entities. And this has some advantages in your processing, because these relationships are already defined. And you don't need to take existing tabular data and do some horrible processing to it, which kind of gets it into the format we need. So that's the first step. But now we also need to process data. Now this is a tool that perhaps divides some opinions. Few groans muttered every time it comes up, but Spark. Graphx is a component within Spark that supports processing graph data. For example, if you're defining the connections in your graph, let's say we're in a supermarket and we want to see which items are bought together. Well, from the data, it's probably clear that actually almost every item is bought together, but we want to ignore the ones which have such weak signals. So we need to then filter our graph. That's where Graphx comes in, makes the processing data pretty easy. And finally, a library to actually help you get more hands-on with the models. PyTorch geometric. Really good documentation, endless notebooks there to help you get started. And I want to also make a mention to a more niche library, PyTorch geometric temporal. So if you can imagine, we've been talking about graphs now, just static graphs, but graphs can also evolve. And so this library combines kind of graph theory also with the concept of recurrent neural networks. So it enables you to capture the spatial element in your problem, but also the temporal. So space and time. I think Einstein would be proud. It's a much smaller library. I don't think it's quite production ready yet, but they are looking for contributors, so maybe interesting if someone is interested in graphs and wants to contribute to such a library. So one of the main takeaways from this talk, I hope, is that graphs can be useful in some situations. They can encode tricky parts of our problems that previously we may have ignored. And with that, I open the floor for some questions. Thank you.
Thank you very much. Okay, can we open the floor to any questions?
Hey, very nicely delivered talk, thank you. I've got a quick question, maybe niche as well, but I've got lots of data that would be really suitable for graphs, but it comes sort of in the form of an adjacency matrix, but it's really noisy. Is it really sensitive to that? So for example, in your bike example, I'm not too certain if the bike came from Mayfair or Westminster, but it's like that across the board. Would it be too sensitive for that or no?
So you say you have a data set in which you have this adjacency matrix?
Yeah.
Okay.
But the nodes themselves are very noisy. So like I've got some noise between Westminster and Mayfair.
Oh, I see.
And
okay,
it could be, you know, it could be this or this. Is it sensitive to that noise, or would it be okay in dealing with it?
It would be okay in dealing with it, but it would slow things down because it's going to be very low signals that then get propagated. So it's just better to zero them out.
Okay, cool, thanks.
Well, it depends on the sensitivity of your task as well. Maybe you cannot zero them out. For example, if you're analyzing fraud, then yeah, maybe don't just remove data points. But if it's for a traffic case, then it's not so sensitive.
Brilliant, thank you very much. I'll make my way around the room.
Thanks for the presentation. I mean, I've missed it, but then I was just thinking, how does this work in cases where you have super nodes in the graph, say particular nodes that have lots of connection with other smaller nodes? Say you want to make predictions for such nodes, does this mean that you wouldn't be able to make the actual accurate prediction since now they are connected to a lot of other nodes? And also for cases where you have smaller nodes without lots of connections as well, say super nodes, and would I call them subnodes if that's
so are these nodes of the same type, or
yes,
you have like
same
two
type.
categories of nodes?
Same type.
Okay.
Yeah. So I was just asking, how does this fare well for such type of nodes with lots of connections with other nodes?
It depends on what the relationships are. It's fine to have like nodes which don't have a lot of connections. And yeah, super nodes, for example. In the social media setting, you can imagine there's few users who have lots of followers, and those followers don't really have any people who are following them. And it works quite well in that case. So I don't think there's an issue with having these super nodes, like you say. But it also depends on what the relationships are. So the answer is it depends.
Okay, I had a question over here.
Hey, thank you for the talk. Regarding this message passing, in your experience, how much time or how difficult is it to tune that, right? So how to come up with one signal from your features, or maybe doing a weighted approach, or?
Yeah, so the best way to do this, I find, is to look at the literature and see what architectures are being used for similar tasks. So in traffic prediction, certain networks have certain architectures. In the fraud case, other architectures seem quite good. So it depends on your kind of use case. So in the case of the fraud, for example, you can imagine there's lots of transactions that happen between people that are like 15, 16, 17 nodes away, but you still want to incorporate that. Then it's quite hard because certain points of the graphs are really far from each other and they never share information. So what you usually do in that situation is by having some kind of like hybrid node that exists on a layer above. And at each step, every node sends that supernode or a combination of supernodes some representation, and then that gets shared across back to the other nodes. And so, yeah, it depends on your problem, but there are ways around that. And so that's an example of how you would solve that problem. But maybe it's, yeah, we can speak afterwards as well to go into more detail.
Hi, really interesting talk. Quite a new area for me, so sorry if it's too simple a question. There are some circumstances where you'd want to know if you were counting how many bikes should be at station 1 versus station 2. If 1,000 people cycle this way and 1,000 people cycle this way, that's great if you're just looking at the station monitoring because it will cancel out. But if you actually want to look at congestion on the road, you'd be treating that differently. How would you handle those things differently?
By handling the case that people are traveling in different ways.
So in some cases, I'm only interested in the actual count of the bikes at the stations, and in some cases, I'm interested in what the traffic flow on the road is.
Yeah.
So how could you differentially weight those two different things?
By having two separate features which define
Just two separate
flows.
features.
Yeah.
All right, we'll have 2 more questions.
Yeah, thanks for the talk. My question is kind of related. So if you had, because in your problem you described just demand at each node, but if you had origin destination information, so you knew like how many bikes went from Mayfair to Tower Bridge, how would you sort of encode that information on top of the problem that you described?
So that would be a relationship between those two nodes, because now you have there's people traveling via the bike schemes between these locations, but it's also people traveling via other modes as well. And so all of this contributes towards potential demand at the location. The more people that go to this particular location, the more likely it's going to be used. That's going to contribute towards demand. So when you encode information on the edges, like I mentioned, you would encode things like distance, but also people traveling between the two via train, traveling between the two via the bike scheme, and other modes.
Okay.
Right, and one more at the front here.
Thank you. Yeah, thanks a lot. Really good presentation. I don't know if you can just briefly kind of clarify. Towards the end, you talked about Node.js, Graphx, and I think PyTorch, geometric. Are those 3 different ways of representing? I mean, I've used Node.js, as a way to sort of, from a database, you can get a graph. And then I wasn't too sure, you mentioned Graphx.
Yeah.
So is that another way of sort of representing graphs using PySpark?
So Neo4j is for storing data.
Okay.
Spark Graphx is for processing the data,
Okay.
pre-processing. And then the PyTorch is for the models itself.
Oh, right, I see.
So
Okay.
the models, they need data in a certain format.
Yep.
And of course, where it's stored and how it is, you need something in between
Correct.
to match those. And that's where Spark comes in.
Okay, thank you. Yeah, sure.
Sorry, that is all the time we have for questions today, but if you could all help me in thanking Usman for a truly enlightening talk.